Good morning, and welcome to today's press conference brought to you by the U.S. National Science Foundation and the Event Horizon Telescope Project. Thank you for joining us. I would like today to introduce today's distinguished panel and guest speaker. Dr. Karen Marrongelle is the Chief Operating Officer at the U.S. National Science Foundation. Excuse me. Feryal Ozel is a member of the Event Horizon Telescope Science Council, a professor of astronomy and physics, and Associate Dean of Research at University of Arizona. Vincent Fish is a member of the EHT Science Council, the Operations Data Manager and Scheduler for the EHT, and a research scientist at MIT Haystack Observatory. Catherine Bowman is co-lead of the EHT Imaging Working Group and Assistant Professor of Computing and Mathematical Sciences, Electrical Engineering, and Astronomy at Caltech. Michael Johnson is a member of the Event Horizon Telescope Science Council and an astrophysicist at the Center for Astrophysics, Harvard-Smithsonian. Our panel is here to present groundbreaking results in our very own galaxy. We will have time for questions after the presentation, so please hold your questions until then. We'll be taking questions both from members of the news media in the audience and online. Media viewing online can submit their questions to eht@nsf.gov. That's eht@nsf.gov. And now I'm pleased to introduce Dr. Karen Marrongelle, the National Science Foundation's Chief Operating Officer. Dr. Marrongelle?
Good morning, everyone, and welcome. I'm sure you will agree, but it seems like just yesterday when, thanks to the incredible efforts of the Event Horizon Telescope, we all caught an awe-inspiring glimpse of the first true image of a black hole. And since that moment, this historic discovery has continued to inspire scientists to ask more questions and to look for even more answers throughout our universe. The Event Horizon Telescope has continued to push the frontiers of science and discovery. And today, because of the incredible work of all those involved, I am honored to join you as we announce another exciting and historic breakthrough. This discovery was made possible by more than 300 researchers from 80 institutions working with 8 different telescopes around the globe. Their achievement is a truly inspiring scientific endeavor and a powerful reminder of what we can achieve through international collaboration and coordination. Even before the program's inception, the U.S. National Science Foundation has played an important role in supporting the fundamental research that makes the Event Horizon Telescope possible. Today's announcement is a proud moment for us all, and we are excited to continue enabling extraordinary science alongside our partner institutions. Together, we are continuing to push the boundaries of what science and technology can achieve and are unlocking more and more of the universe's greatest mysteries. So thank you. And now, it is my pleasure to introduce Feryal Ozel from the University of Arizona, who will talk about these exciting new results.
Good morning, everyone, and thank you for being here while we share with you our exciting new results about our galaxy, the Milky Way. Our home in this universe, what fills our night sky on a dark summer night. At its heart, towards the constellation Sagittarius, is Sagittarius A star, the supermassive black hole suspected to reside there. a source that has been a focus of intense astronomical studies for decades. Observations of stars orbiting around it revealed the presence of an object that is very massive, 4 million times the mass of our sun, but also very faint. For me personally, I met it 20 years ago and have loved it and tried to understand it since. But until now, we didn't have the direct picture confirming that Sagittarius star was indeed a black hole. Today, the Event Horizon Telescope is delighted to share with you the first direct image of the gentle giant in the center of our galaxy, Sagittarius A star. This image shows a bright ring surrounding the darkness, the telltale sign of the shadow of the black hole. Light escaping from the hot gas swirling around the black hole appears to us as the bright ring. Light that is too close to the black hole, close enough to be swallowed by it, eventually crosses its horizon and leaves behind just a dark void in the center. Getting to this image wasn't an easy journey. It was one of building a worldwide telescope array and a global collaboration. One of getting and processing petabytes of data collected from those telescopes. Of imaging algorithms more complex than many that have ever been developed. What made it extra challenging was the dynamic environment of Sagittarius star, a source that burbled and gurgled as we looked at it. And the challenges of looking not only... something is advancing the slides without... Can you please go back to the earlier slides? Let's see if this will work. What made it extra challenging was the dynamic environment of Sagittarius star, a source that burbled and gurgled as we looked at it. And the challenges of looking not only through our own atmosphere, but also through the gas clouds in the disk of our galaxy towards the center. It took several years to refine our image and confirm what we had, but we prevailed. The HD collaboration has indeed been hard at work, imaging black holes with exquisite resolution using new techniques. In 2019, we revealed the very first such image, that of the supermassive black hole in the M87 galaxy. That black hole is 1,500 times more massive, making its horizon 1,500 times larger. But it is also 2,000 times further away from us. This makes the two images appear very similar to us when we gaze at them in the sky. But the two black holes couldn't have been different from each other in practically every other way. The one in M87 is accumulating matter at a significantly faster rate than Sagittarius star. But perhaps more importantly, the one in M87 launches a powerful jet that extends as far as the edge of that galaxy. Our black hole does not. And yet, when we look at the heart of each black hole, we find a bright ring surrounding the black hole shadow. It seems that black holes like donuts. I wish I could tell you that second time is as good as the first when imaging black holes, but that wouldn't be true. It is actually better. Now we know that it wasn't a coincidence. It wasn't some aspect of the environment that happened to look like the ring that we expected to see. We now know that in both cases, what we see is the heart of the black hole, the point of no return. These two images look similar because they are the consequence of fundamental forces of gravity. Space-time, the fabric of the universe, warps around black holes in exactly the same way, regardless of their mass or what surrounds them. This is what we had hoped to find, given the predictions of Einstein's theory of general relativity. And it is exactly because of this fact that we are able to use these new observations, the image of Sagittarius star, to perform one of the strongest tests of general relativity to date. What was remarkably helpful to us when performing this test was the amount of information we already had about Sagittarius star before our observations. The astronomy community has monitored for decades the motion of stars around the dark center of the galaxy. By tracing these orbits, we have come to know the mass of the black hole with extreme precision. That allowed us to make a prediction for how big the image and the black hole shadow should be, if Einstein's theory is right, with no wiggle room and no parameters to adjust. The only way to change the size of the shadow is if we change the theory. And what we found was that our image was in very close agreement with theoretical predictions. These observations leave us very little freedom to change Einstein's theory of gravity. Now we have two laboratories in the sky, M87 and Sagittarius star, for exquisite tests of extreme environments. We learned so far that we understand gravity pretty well. But as you will hear later, as sophisticated as our simulations are, we discovered that we still have a ways to go with modeling their turbulent environments. Now I'd like to introduce Vincent Fish from MIT Haystack Observatory, who is going to tell us how this was accomplished.
Imaging a black hole is a task that's too big for one individual or a single observatory. As we found out the first time around, it's a lot of work. Large teams of people have to pull together to handle the science, engineering, and operations. It also requires many telescopes. To distinguish the ring-like structure in Sagittarius star, our telescope had to be almost as big as the Earth. Fortunately, the technique of interferometry allows us to link pairs of telescopes that are very far apart into the equivalent of a planet-sized telescope. We use this technique both for Sagittarius star and the black hole in M87, or M87 star as it's called. But these two black holes are quite different from each other, as Feryal described. And for reasons Katie and Michael will explain, imaging Sagittarius star turns out to be a lot harder. Today's results come from the same 2017 observing run as M87 star, but with a big difference. The South Pole Telescope at NSF's Amundsen-Scott South Pole Station observed Sagittarius star, whereas M87 star was completely out of view. So while we had 7 telescopes to see M87 star, all 8 could see Sagittarius star. The South Pole Telescope is perfectly suited to observe Sagittarius star, both because it can see it continuously and because it significantly increases the resolution of the array. In interferometry, each radio telescope is at a different location. By correlating their signals and studying the resulting data, we can reconstruct images of the source. The more telescopes, the better. The farther apart they are, the more we can zoom in on the source. Turning pairs of telescopes into the nodes of an interferometer is a process similar to everyone shaking hands with everyone else in a room. You need at least 2 people, and the number of handshakes grows very quickly as you add more people to the group. So the amount of data we get also grows very quickly with each telescope we add to the EHT. When we observed Sagittarius star, 8 telescopes collected around 3.5 petabytes of data. That's equivalent to about 100 million TikTok videos. It's way too much data to stream over the internet. We actually have to ship hard drives around. But just gathering the data isn't enough. The data has to be carefully combined, calibrated, and converted into an image, with teams of scientists, many of them right here in this room, working on each stage of the process. After the observing sessions, teams from each site ship hundreds of hard drives back to the correlation centers in Westford, Massachusetts, and Bonn, Germany, where supercomputers combine the signals and produce raw input data. The calibration team combines the raw data with information about the sensitivity of each telescope to form the data used by the imaging teams. And then the imaging teams process the information using a variety of methods to reconstruct the best possible images of the hot plasma surrounding the black hole. Other teams then extract features from the image, and so other teams run massive simulations based on prior physics studies that predict how material behaves around black holes on the scale of Sagittarius star. Coordinating all those intensive efforts to image M87 star was already incredibly difficult, and the global pandemic emerged right as we pivoted to Sagittarius star. The pandemic slowed us down, but it couldn't stop us. Our collaboration meetings and workshops were moved fully online, but there's no substitute for getting together in the same room and working through hard problems. But Sagittarius star brought a number of new specific challenges, even though it is closer to Earth. First, M87 star doesn't change very quickly, but Sagittarius star does. In this sequence of model images, 1 second is equivalent to almost 2 days. Imaging a rapidly spinning turbulent source like Sagittarius star is a lot harder than it was for M87 star. As Katie will describe, material swirls around M87 star over the course of many days, but it takes only a few minutes for material to move around close to the horizon of Sagittarius star because it is much smaller. It changes quickly, so we had to collect our data quickly. To further complicate things, we see Sagittarius star through an enormous amount of material in our own galaxy, which scatters the radio waves and blurs the image. But years of observations at other wavelengths have made it possible for astronomers to partially mitigate the effects of this blurring. The result is an image that, until we finished our analyses, we were never sure we could get. Our collaboration's remarkable image of Sagittarius star and our scientific conclusions were a combined effort that involved not just the handful of us on stages around the world today, but more than 300 people all working together, united by our fascination with black holes. We are especially grateful for our students, postdoctoral researchers, and early career scientists who worked very long hours to produce these results. Yet the EHT collaboration does not operate alone. As detailed in our 6 papers, we work together with other teams of astronomers observing signals across the electromagnetic spectrum, from radio waves to infrared and X-rays, all of which provide us with important context to understand the image. Our results build upon decades of studies by other groups that establish that Sagittarius star contains a dark, massive object, characterized its properties, and retained accurate measurements of its mass and distance. We especially want to recognize the hard work by Nobel laureates Andrea Ghez and Reinhard Genzel and their teams studying the orbits of stars around the galactic center. Some scientific results are the work of small teams. Imaging Sagittarius star took an entire planet. And now I'd like to introduce Katie Bauman of Caltech, who will talk about how we captured this black hole image.
Today, we are thrilled to reveal the very first image of the supermassive black hole at the heart of our own Milky Way galaxy. This image from the Event Horizon telescope required more than just snapping a photo from telescopes at high mountaintops. It is the product of both technically challenging telescope observations and innovative computational algorithms. Taking this picture proved even more challenging than imaging the M87 black hole, which we revealed to the world back in 2019. To understand why, let's go back to how our telescope works. As Vincent mentioned, the EHT doesn't work like a regular telescope. Instead, our radio telescope shakes hands. They work in pairs, with each pair contributing a little bit of information to the entire image. Telescopes that are far apart can detect the smallest, sharpest features of the image. Orientation is also important, with each angle picking up different parts of the whole. Telescopes that are closer together become sensitive to the broad features of the image that the wider pairs can't see. And combined, these components of the image can provide a good representation for the target we're observing. Making a perfect image would require telescopes at all different orientations and separations. But EHT's 8 telescopes scattered around the globe only capture some of these potential pairings. Luckily, as Earth rotates, the projected separations and orientations between the telescopes change, providing more, but not all of the information we need to make a perfect picture. As Michael likes to say, taking a picture with the EHT is a bit like listening to a song being played on a piano that has a lot of missing keys. Since we don't know when the missing keys should be hit, there's an endless number of possible tunes that could be playing. Nonetheless, with enough functioning keys, our brains can often fill in the gaps to recognize the song correctly. This was also the case for imaging M87 star. But for Sagittarius star, there was another daunting challenge that we couldn't ignore. The hot gas spiraling around these 2 black holes moves at roughly the same speed. But where gas takes days to weeks to orbit the much larger M87 star, for Sagittarius star, because it's a lot smaller, gas can make a full orbit around its event horizon in mere minutes. And that means as we were collecting data during the Earth's rotation, the material was swirling around Sagittarius star so quickly that Sagittarius star's appearance could change from minute to minute. This is a bit like changing the key of the song as we are playing it on our broken piano. We had to address all those challenges, along with many other challenges that I don't even have time to get into, like the fact that we're observing the black hole through Earth's turbulent atmosphere, as well as the galaxy's gas. And to tackle these challenges, we spent years developing computational imaging algorithms that allowed us to recover a picture of the center of the Milky Way with the collected incomplete data. But the question remained of how do we fill in that missing information? To capture the range of potential Sagittarius star appearances, our team produced tens of thousands of different images with different methods that filled that information in differently. Each of these images is slightly different, but they are all consistent with the EHT data. By averaging these images together, we're able to emphasize the common features appearing in most of them. And here, a bright ring clearly pops out. But it's important to note that not all the images that we recovered looked alike. In fact, we found that we could cluster the recovered images into 4 categories based on similar visual features. 3 of the clusters contained a ring-like feature with only differing brightness around the ring. However, there existed a much smaller 4th cluster that contained a variety of images that did not appear ring-like. Although these non-ring images couldn't be fully ruled out from the data alone, the vast majority of the images that our algorithms recovered had a ring shape. And through literally years of exhaustive tests on both real and simulated data, we're now confident that there is compelling evidence that the true underlying structure is a ring. A detailed analysis of the images has revealed that they all share the same ring size, a size in perfect agreement with prior observations in theory. 50 microarcseconds, or in other words, a size 1/13 billionth the span of our night sky. Coming to this conclusion took years, but we never backed away from the challenge. And through the power of computational imaging, the EHT team overcame seemingly impossible hurdles to capture the first image of the beastly black hole at the heart of our galaxy. And now I'd like to introduce Michael Johnson from the Harvard-Smithsonian Center for Astrophysics to discuss what this picture of the black hole teaches us and our excitement for the future.
The EHT has turned the center of our galaxy into a cosmic laboratory. We are peering into a new environment, the curved spacetime near a supermassive black hole. And it is teeming with activity, always burbling with turbulent energy and occasionally erupting into bright flares of emission. And our first step in making sense of the physics of this environment was to move from images to measurements. So we developed tools that locked in on the bright rings in all those images that Katie showed and measured their properties. We also developed a set of simple models that we could fit directly to the EHT data. Now, this is a different approach than imaging, so it gives us a different perspective, and it lets us understand the systematic biases of both methods. Because these simple models are easier to constrain with very limited data, we fit them in two ways. So in the first way, we divided our data up in time, and then we fit a series of nearly instantaneous snapshots. This ensures that our measurements aren't being contaminated by the variability of Sagittarius star. And we then combine all of those snapshots into a single average model. In the second way, we fit a model to all the data at once. Here we're fitting for the average image structure, along with an extra source of variability noise that's sitting on top of that average. And this procedure is very similar to what we did to make the images. By combining all of these different approaches, we were able to precisely characterize the properties of the ring. And we found that we can measure the ring diameter to an accuracy of about 5%. We also use these methods to quantify the features that aren't seen directly on the images. So as Feryal mentioned, the orbits of stars have given us an exquisite measurement of the mass of Sagittarius star, about 4 million times the mass of the sun. And Einstein's theory of general relativity then predicts exactly what size shadow the black hole should cast. So this theoretical feature, the shadow, is the image of the event horizon. It's our line of sight into the black hole. So the blue ring that you see here is the predicted shadow diameter from the stars. And that band is showing the range of possible values. Most of the uncertainty here is actually because we don't know whether or not the black hole is spinning, and the spin has a small effect on the shadow diameter. So the stars gave us a tight prediction for something that was completely unseen. And we didn't know if the EHT image was going to match this prediction. But we found that these two completely different views of the black hole, one relying on the motion of stars and one relying on the bending and capture of light, were perfectly aligned. This is an extraordinary validation of general relativity. Next, we wanted to study the turbulent environment around the black hole. So we turned to supercomputers. A large team across the EHT, including many people here in this room, created a whole zoo of numerical simulations of black holes. These let us see mock movies of what a perfect instrument might observe for Sagittarius star. With these simulations, we can move to any viewing location around the black hole. We can look at the black hole edge-on, as you see here, peering through the disk of material that's flowing onto the black hole. Or we can tilt our camera at any other inclination and view the black hole face-on from above. We can also vary the properties of the black hole itself, allowing it to sit still or spinning it up to a maximum rotation set by the speed of light. And we can also vary the properties of the magnetic fields and the gas near the black hole, simulating weak and turbulent magnetic fields or strong and dynamically significant fields. With this enormous library in hand, more than 5 million simulated images in total, we can play a game of galactic center Guess Who. So a few simulations have too much diffuse emission in the disk around the black hole. And so we can reject those. There they go. Most of these have rings that look different than the ring on the EHT image, so we reject those too. Some of them produce too much light at other frequencies. And some of them have bright outflows that we don't see in the galactic center at longer wavelengths. So we're left with only a handful of simulations that can describe nearly all the features that we observe. And these simulations reveal an absolutely remarkable environment. First, we see that only a trickle of material is actually making it all the way to the black hole. If Sagittarius star were a person, it would consume a single grain of rice every 1,000,000 years. And while some black holes can be remarkably efficient at converting gravitational energy into light, Sagittarius star traps nearly all of this energy. Only 1 part in 1,000 is converted into light. So despite looking so bright on these simulated images, the black hole is ravenous but inefficient. It's only putting out a few hundred times as much energy as the sun, despite being 4 million times as massive. And the only reason we can study it at all is because it's in our own galaxy. And this is why Sagittarius star is such a precious target. While M87 had one of the biggest black holes in the universe, and it launches a jet that pierces its entire galaxy, Sagittarius star is giving us a view into the much more standard state of black holes, quiet and quiescent. M87 was exciting because it was extraordinary. Sagittarius star is exciting because it's common. These simulations also tell us that we're looking close to face-on at Sagittarius star. You can see this directly in our images, which have fairly uniform rings. And this is surprising. Even though we're peering through the plane of our galaxy to look at this black hole, we see the black hole's not aligned with the galaxy. It's actually tilted towards us. These new results are a triumph of computational astrophysics, creating models that can reproduce nearly all the properties of Sagittarius star that we observe. But we're seeing cracks in the foundation. None of our simulations is consistent with all the properties of Sagittarius star. In particular, our simulations are too variable. We've actually had trouble simulating a source that is as quiet as Sagittarius star. So this is driving us to making even better measurements and sharper images. And the first challenge we need to overcome is the scattering. So even with a perfect instrument at 230 gigahertz, this is the kind of image that we would see on the sky. This image is fuzzy because of the effect that Vincent mentioned. We're looking at Sagittarius star through the arms of the Milky Way, and this is kind of like peering at it through frosted glass. Because of the scattering, the crucial image details, such as the sharp ring that comes from light that's bent all the way around the back of the black hole, are lost. But with support from the National Science Foundation and other partners, we are already pushing our instrument further and going to even more challenging observations at 345 gigahertz. These will cut the effects of scattering in half, producing much sharper images. And we're not stopping there. We are already designing a next-generation instrument, adding many new telescopes around the world to the EHT. And this improvement will help us move from these still images to capturing the first high-resolution movies of black holes, letting us witness them in action and continuing this quest toward the boundary of the unknown. Thanks. Yeah.
Thank you all. We'll now take questions from members of the news media until 10 a.m. Please raise your hand, wait for a microphone, and identify yourself and your outlet. Please ask one question and hold follow-up questions so everyone has an opportunity to ask. If you're viewing online, submit your question to eht@nsf.gov. Every third question will be from reporters viewing online. Please be sure to include your name and outlet with your submissions. We are here today to talk about the amazing results presented by our panelists about Sagittarius A star. Any question not related to the result will be directed to the cognizant subject matter expert after the press conference. We'll follow up with any questions or topics we cannot cover today. With that in mind, we're ready to take questions. Please remember to say your name and outlet.
Thank you. Seth Borenstein, the Associated Press. I guess more for Dr. Ozel, but you described SAG A star as a gentle giant and quiescent, but Dr. Bowman called it beastly. There's sort of a general public view of black holes as this horrible, violent, scary, dangerous place, where nothing escapes from. Is what you're seeing more peaceful than what the lay people think of as black holes, and is it changing the way we should be thinking of black holes, or is it still a real violent place, just comparatively less violent?
That's a very good question. Thank you. The way black holes behave depend a little bit on the amount of material that is falling onto them. The one in the center of our galaxy, Sagittarius A star, is actually, as Michael mentioned, eating very little. And because of that, its environment is relatively gentle. When we say that, of course, the temperatures and magnetic field strengths are still quite high. So that is leading to, and the motion of the gas around it is still turbulent. So that is leading to the kind of burbling and gurgling that Katie described. And that is making our imaging and our life when we're trying to get a still shot of our moving object a little bit difficult. But in reality, when we talk about the turbulent environment of a black hole or any object, there are actually two types of things we think about. Time scale and just how much it varies, how much the brightness varies. And what Sag A star showed us is that our predictions for how much it should vary was actually too much. So it turned out to be a gentler, more cooperative black hole than we had hoped for in the past decade of simulating its environment. So we love our black hole.
Next question. Name and outlet, please.
Hey, it's Seth Fletcher with Scientific American. Were you able to measure its spin?
I can comment on that briefly. So we simulated all these different movies, and some of those had non-spinning black holes, and some of them had spinning black holes. It turns out that all of the ones where the black hole wasn't spinning were ruled out. So our simulation library is giving some evidence that the black hole is spinning. Now, what we'd really like is to be able to point to something on the image and say, oh, that little feature, that's how we know it's spinning. Something like the shape of the ring, the sensitivity of spin. But we don't have that level of sensitivity right now. So the simulations are pointing us to the conclusion that the black hole is spinning, but that's something that's going to be a topic of intensive study over the coming decades.
Great, thanks.
Thank you. And we're going to take an online question now from Ed Brown from Newsweek. Now that the EHT has achieved its primary goals of imaging M87 in Sagittarius A star, what is next for the project?
I can take this. So far we have static images of M87 star and Sag A star. But as you see in the simulations, there's a lot of exciting physics to be gotten at by making a movie. And so we want to watch material move around these sources. M87 star will be the easier source for this. It sits still for its photograph. You take a picture today and you throw all of your data together in the pot and make a nice image. But that also means that you need to wait a while for it to move. And so the Event Horizon telescope has up to this point operated in kind of a campaign mode where we observe a few nights out of a 10 to 12 night window. And over that time, M87 just barely turns, barely changes. We have a series of technical developments at the observatories that will allow us in a couple of years to be able to switch observations on and off pretty easily so that we can observe it for months at a time and actually see it move. Sag A star is harder, and maybe you want to talk about technique and Michael on
Sure.
telescopes.
Yeah, so as Vincent said, like one of the big goals for us going forward is not just to see a still image of the black hole, but actually see the black hole as it's evolving, as the gas is slowly falling in towards the event horizon. And to that end, we did try this with the 2017 data. We tried to use the data that we got to try to recover a movie. And so we developed algorithms that allowed us to not just make static images, but movies. And we applied these to the data. And we saw that although there was something interesting there, that the data that we currently have doesn't constrain that movie enough in order to say something that we're really confident about. So there's definitely exciting stuff there, but we're looking towards the future in not just improving our methods, but also the telescope observations that we actually collecting more data so that we can show you something that we're confident about. Michael, I don't know if you want to talk about future.
Well, it's hard to convey just how much more information there is here. So, progressively, here you're only seeing the total intensity of the light that's being emitted. Our next step will probably be to make polarized images of Sag A star. We can see the magnetic fields near the black hole and see how they're dragged by the black hole itself. In addition to that, this is a single color image. We're denoting brightness by the color here, but it's really sort of some equivalent of a black and white image for us. And so we're looking at expanding to observing with multiple frequencies to really see an image in color. And that will tell us enormously more about the source. And then we're adding all these new telescopes. I mean, we know that there's more to see here. We know that there are sharp features that are tight predictions from general relativity. This is how we can push our theories further. And so we're hoping to add these new telescopes around the world and be able to really dig into those sharp features and to be able to see these high-resolution movies.
Thank you. Next question from the audience.
Hi, Camille Carlisle, Sky and Telescope Magazine. So I'm curious if you can go into a little more detail about what these observations tell us physically about Sagittarius stars. So you hit the spin a bit, the viewing angle, which threw me and matches gravity. But can you go into the accretion flow a little more? Like, what does this tell you about? Is it fluffy? Is it puffed up? Why are there 3 bright spots?
Maybe, go ahead, yeah. Sure. Well, I'll say one thing I didn't mention that we concluded was we did learn about the magnetic fields near the black hole. And so the simulations that were successful all have strong dynamically significant fields. This is a little, it's pointing this paradox of is it gentle or not. I mean, these are very strong magnetic fields to the gas around the black hole, but they're weaker than the magnets on your refrigerator. So it's, everything is relative. So we are starting to get this view of what the magnetic fields in the gas are like. And maybe Feryal, you want to comment more on the accretion properties and the knots?
Sure. Yeah. So we are confirming, for example, that the accretion rate onto the black hole is low. And we're getting a first glimpse that the temperature in the flow is the temperature of the electrons, not just of the ions in the flow, is quite high. The simulations that Michael showed that pass all the tests tend to be these stronger magnetic fields and higher electron temperature flows. So this is the first glimpse we have of what fits and what doesn't fit in this giant library of simulations. And the second part of your question is, what about the knots? When we look at these simulations, it is natural to expect brightness changing in a knotty way around the black hole. So that is something that's theoretically expected, for example, when a part lights up because it's more magnetically dominated, or a feature in the accretion flow is brighter than the rest. However, in our case, we don't trust the knots that much. In Katie's simulations of the top set, what we call the top set, all the different ways of filling in the missing information, you may have noticed that the knots move around a little bit. And those knots also tend to line up with the directions in which we have more telescopes. So even though from a theoretical point of view it's natural to expect these brighter spots, in our images we don't trust them to that extent yet.
Next question from the press.
Hi, Marina Corrin from The Atlantic. Can each of you talk a little bit about how this picture makes you feel? One particularly exciting thing about this result, unlike with the black hole in M87, is that this supermassive black hole is ours. So when you look at this image and you take off your scientist hats, what comes to mind for you?
I think that, well, there's 2 sides to this. One is that I think every once in a while, we've been working on this for so long. I mean, with so many people, you know, every once in a while, you just have to pinch yourself, and you're like, this is the black hole at the center of our galaxy. Like, you kind of forget that every once in a while. And that's pretty amazing. It's pretty amazing what we were able to do by bringing together people with lots of different expertise, and that we were actually able to do this. And so for me, that's just, I don't know, I just feel really proud of everything that we've done. So as a member of the collaboration, I just am very proud that we've been able to kind of, you know, didn't let all these challenges that were there from the beginning, didn't let us stop us from still going after that. We weren't afraid of the uncertainty and all the missing information and all this. We figured out ways to deal with it. And for that, I'm really, really happy, and I'm so honored to be able to work with the people here. But otherwise, yeah, I mean, I think it's just super exciting. I mean, what's more cool than seeing the black hole in the center of our own Milky Way? So I don't know what other people feel.
Yeah, it's, I've been with the project now for almost 15 years, and it's been exciting watching, watching the project evolve, watching the collaboration grow. You know, in the early days, it was a real struggle just to detect Sagittarius star. And the signals were so noisy that you couldn't even think of imaging. You didn't have enough telescopes. You know, it seemed like a hopeless task at the time. I remember the first detection of M87 a couple years after that. And now we have built out the array. We've instrumented a lot of telescopes with wide bandwidth equipment. We have phased up ALMA and the submillimeter array, and now NOEMA in France. We have new telescopes join, and the data get better and better. And what seemed like it was going to be an impossible task is now, well, it's still hard, but it's doable.
Yeah, I'm one of those people who has thought about Sag-A-Star for a long time. 22 years ago was my first paper on it when I was a graduate student. So I feel like I had this remote friend that I kind of had an idea in my head about what it looked like. We were online chatting, and then I was like, oh, you're real, meeting in person. So it's a very nice feeling.
I'll say, I really like what Feryal said in the intro. We had this prediction for Sag-A-Star that had no wiggle room. The stars gave a very precise measurement of exactly what we should expect. And so I remember seeing this and just kind of walking around in a daze. You look at that image, and that hole in the center has 4 million solar masses. That's incredible. And there was doubt for black holes for decades after they were first derived as a mathematical solution. Everyone kind of assumed that they just evaporate once we understood more. It doesn't feel like they could exist in nature, and I think that sort of persists for us. You're always waiting for something to step in and say, okay, of course, black holes they're just science fiction. There's something else there. So really just that certainty that we understand what we're seeing was really special for this image.
If I could add to what Michael just said, 4 million times the mass of the sun, and the scale of that image would fit in the orbit of Mercury. So when we imaged M87, which is 1,500 times more massive, that's the size of the solar system. Now we're getting to the size of the innermost planet in the solar system, and smaller than the orbit of Mercury. 4 million times the mass of the sun. It's all in there.
Thank you. Dan Verano from BuzzFeed asks, how does the image advance our understanding of black holes or physics, or does it just confirm what we already thought? Okay, let's move to...
No.
Okay.
So it's a good news and bad news story, I think. The great news is that we keep pushing the limits of how we can test our theory of gravity, which we really expect to break down somewhere. We know about the incompatibility with the microphysics. We know that it should give us a hint at some point of maybe something different than how we formulate the theory of gravity with general relativity right now. And yet we keep pushing to different scales of mass, all the way from stellar mass black holes with LIGO to Sag-A-Star in the middle to M87 at 6 billion solar masses. And we go to as close to the horizon as our telescopes allow. And we don't see a crack in that theory yet. We are hoping it will show up somewhere. But at the same time, it's the first time we're trying to really test our models of the environment of black holes. How do they accrete mass? How do we understand that plasma? And as Michael was discussing, that's not perfect yet. So we've learned actually quite a bit about what might be missing from our simulations at this point.
Thank you. Question from press in the audience? Okay, we have any, did you want to follow up question?
Could you talk a little bit more about how this image reconstruction process was compared to M87? Like, you had to change your algorithms to handle a completely different time scale. What went into that?
Yeah, imaging Sag-A-Star was a bit of a messier story than imaging M87 stars. So for M87, it was like, this amazing thing. We had split into these different teams, and we had independently imaged, and we came together, and it was all the same, and we all celebrated. And then, we worked hard to make sure that we hadn't screwed up and stuff. but it was a very clear-cut story. But in Sagittarius Star, we started with the same process. We started with the different imaging teams and everything. And what we found is the imaging teams were like, I don't want to show my image, because like, we couldn't figure it out. Even within every imaging team, it wasn't very clear. And so then when we came together, we saw, okay, well, mostly the imaging teams are seeing these rings, but maybe, but there's this other stuff there, and what's going on with that? And so that's really, what we have spent years trying to figure out. Why is this? And we couldn't just get at it by just looking at the data. We really had to understand how our methods work in different kind of situations. So for that, we developed, not just developing new methods that had to deal with the variability and stuff, but also developing simulations where we could actually make mock data sets as if we were actually observing something that was evolving kind of like Sagittarius Star, and seeing how our methods worked in those situations. And one thing that built a lot of confidence in us is that we saw, even when we made a data set and we pretended that we had made observations of it with the Event Horizon telescope, adding all the different kinds of crazy noise into it and everything, we also saw that we recovered sometimes non-ring shapes at a similar percentage of the time that we did with Sagittarius Star data. So here we knew when we know it's actually the true underlying source is a ring, our methods sometimes break down. And so things like this helped us build our confidence. So it wasn't the clear-cut story like we had with M87, but it makes it more, it gave us a challenge and we learned a lot in it. And I think, and hopefully that will help us improve in the future going forward.
Thank you. Next question, name and outlet, please.
Yes, thank you. Seth Bornstein, again at the Associated Press. For Dr. Ozel, well, you said this is very hot. Can you give us sort of a little more detail? How much? What type of temperatures are we talking about? How does that compare to other, temperatures in our galaxy? And I know this is going to sound a very silly question, but my editor is also asking this. You talked about burbling, and was that other word yurgling with a Y?
It might very well be a made-up word. I said gurgling, like a baby sound with a G, yes. But if it is a made-up word, you can change it to whatever you like. So the temperatures we're talking about are really high. I don't know what to compare it to, because we are talking about, for the ions, what is 10 to the 12 Kelvin? Like, somebody help, a lot. It's 10 to, yeah, trillions of Kelvin, trillions of Celsius, yes. And what we are seeing is that, and what we suspected for a long time through numerous theoretical studies that tried to explain the earlier data on Sagittarius Star, is that the electrons in that flow in the same space are also hot, but not as hot as the ions in that space. So it is so hot that, of course, electrons are stripped from hydrogen and helium, so we have a plasma, a mixture of just ionized particles. And the mechanisms that transport heat to the ions and the electrons are a little different, and the electrons can cool where the ions can't. So yeah, we're talking about trillions of Kelvin for both cases, but the electrons being a little cooler.
Thank you. Next question is Roberta with G1 TV Global Brazil. Why was the first ever black hole image blurry, and should we expect to see more detailed images?
Well, I would say it's blurry. Wait, did you say it was for Feryal, though?
Oh, for anyone.
Oh, okay. So it's blurry. We're pushing our instrument to its limit here. So every telescope has something we call the diffraction limit. It's the finest features that it can see. And that's basically the level that we're seeing here. It's fuzzy because to make a sharper image, we need to move our telescopes further apart, like Vincent and Katie talked about, or we need to go to higher frequencies. So we don't think that the black hole is actually a blurry image on the sky. This is just, if you take your glasses off or, have fog or something that's obscuring your vision. We're just at our breaking point here. Yeah.
But I want to highlight that this image is actually one of the sharpest images you've ever seen. It looks blurry on the screen because we only are seeing a few pixels, but actually it's one of the sharpest images ever made.
Great. We have Alicia Sowers, a space reporter from Mashable. Did you learn anything from imaging Sagittarius A star that defined the most current scientific thinking about supermassive black holes?
Sorry, can you repeat the question?
Sure. Did you learn anything from imaging Sagittarius A star that defined the most current scientific thinking about supermassive black holes?
I'm not sure if this is the most current, but we know that black holes, supermassive black holes, exist in different environments throughout the universe. We know that they start forming very early. We don't exactly know through what mechanism. Is it single, very massive stars, or is it clusters of stars that start becoming the seed for these supermassive black holes? But throughout cosmic time, they evolve with their galaxies. It's a very dynamic give and take between the supermassive black holes at the centers of galaxies and their environments. And they go through periods where there is a lot of material around them. So they go through these quasar phases where it is more powerful. I would not want to be near a quasar. And then they go through these quiescent phases, like the one in the center of our galaxy, where matter is just trickling in, and they go through a different type of environment that actually allows us to image the way the Event Horizon Telescope images. We would not be able to image a quasar with our techniques, but we are able to image black holes like Sagittarius A star and M87 with our techniques. So I think in terms of contributing to our understanding of the diversity of the environments and just being able to probe how this process works and how black holes grow, it is a pretty current understanding, I would say.
Great, thank you. Do we have any press in the audience who'd like to ask another question?
Hi, Lucy Obo for AFP. So 2 questions. You talked a lot about a future film, a movie of a black hole. When could we expect that? Could you give us any clue of when do we expect it? And the second question might sound a bit silly, but why is it at the center of our galaxy? Thank you.
I'll take the first one. So for M87, we hope to be able to switch into what we call agile observing, switch telescopes into the VLBI mode for the EHT, and then you take your observation, they can go back and do their other science the rest of the time in 2024. Now, that doesn't mean a movie in 2024. The data have to be processed, and who knows what sort of imaging techniques, dynamic imaging techniques will have to be developed for that movie. But a few years after that for M87. And you had a second question?
Why is it at the center?
Yeah. Do you want to take that?
Dynamical fiction, anybody?
Go for it.
What was the question?
Why is it residing
Why
at the
are
center of the
black holes
galaxy?
at the centers of galaxies?
Okay, so the center of the galaxy is a pretty interesting place. The Milky Way, it's a spiral galaxy. It's like a lot of things in astronomy, it's fairly flat. In the center, it's dynamically relaxed. So the black hole is sunk to the bottom. There's stars zipping around in all sorts of directions. And yeah, it's sitting right there at the very heart of the Milky Way.
Thank you. So we're at 10 o'clock. I'd like to thank you all for attending. If you have further questions, staff from the National Science Foundation is here to assist you. Thank you for joining us today, and this concludes our live stream.
So, Cassie, we just wanted to say, the panelists have mentioned many times, that this is